In this video, we're going to go on and prove the division algorithm for polynomials. In other words, we're going to prove that if we have two polynomials, a of x and b of x, in a polynomial ring f bracket x, where f is a field, we do need that ring of coefficients to be a field, and b of x is non-zero, then there is a quotient and a remainder polynomial in f bracket x, satisfying the same equation we saw earlier, a equals bq plus r, and r of x is smaller than b of x in terms of degree. So the degree of r of x is smaller than the degree of b of x. And I've just made a note here, sometimes the remainder will be 0, and that still fits into this theorem because we consider the degree of the zero polynomial to be negative infinity. So let's get started with the proof. We're going to use the same thinking strategy we did last time. So in the last video, we had a polynomial, and it was a cubic. I think it was x cubed minus 4x squared plus 7x plus 11. And we were dividing by x minus 5. And our approach was to find multiples of this polynomial, our divisor, that we could take out of what was left of our dividend. Again, this is dividend. This is the divisor. And we do this iteratively until the remainder we have left is as small as we can get it. Now, one way that we might approach the proof in general is we might talk about what happens if we set up the notation of the standard algorithm that we talked about in the last video and then perform the process that we did on that standard notation. But we're actually not going to do that in the proof because the notation isn't really essential to the idea of the theorem, and it's not even really essential to the idea of the algorithm as we saw in the last video. You can do it with the standard notation, or you can just iteratively subtract things using your own algebraic reasoning. And the proof is going to read a little bit more like that. The other thing about the proof that's going to look a little bit different from what we did last time is last time we were dealing with specific polynomials, so we could actually carry out specific steps and see how the remainder developed. In this case, we can't do that. And because we're talking about an algorithm that may have 1 step or 2 steps or 100 steps, depending on the degree of the polynomials involved, we're probably going to have to use a technique like induction to show that the algorithm will finish in finite time. So in other words, rather than showing how the 1 step or 2 steps or 100 steps play out, we're just going to show that we can get our polynomial, whatever our dividend is. So again, this thing, we're going to show we can get this down to something of smaller degree, unless our degree is already small enough in the remainder. And by induction, that'll be enough. So actually, rather than using induction, we're going to use an equivalent to it, which is well ordering. So well ordering, just as a reminder, and a non-empty set of natural numbers has a minimum. We're going to use that here. And that's morally like using induction. So rather than inducting and starting with a base case and going up, we're going to show that we can take any remainder as long as it's not already satisfying this condition and reduce it. All right, so here's going to be our approach. We're going to let a of x and b of x belong to f of x with b of x non-zero. And we're going to define a set. A subset S of f bracket x by S equals the set of all a of x minus b of x, p of x, such that p of x belongs to f of x. And that's going to be our set of all possible remainders. And when I say possible remainders, what I mean is this is the set of all polynomials I can get by taking this dividend, a of x, the one that we're starting with, and then removing little packages or bundles of b of x, kind of like we did in the last video. All right, so that's not to say that every remainder in this set is going to be what we're calling small enough. There may be remainders of very large degree. In fact, there will be, because p of x can be any polynomial we want. Its degree could be huge. So S will contain a lot of polynomials, not just the remainder that we want. But the remainder that we want, if it's in there, assuming it's in there, and we'll prove that it is going to be the one with the smallest possible degree. All right, so first of all, we know S is non-empty. Since after all it contains a of x So there must be a polynomial in S of smallest degree, or minimum degree. And we're going to call that R of X, and hope that that's exactly the remainder we want. All right, so since R of X belongs to this set S, it can be expressed in the form R of X equals A of X minus B of X, Q of X, for some Q of X in F bracket X. Now, why am I doing that? Well, first of all, I know that R of X belongs to this set, and what it means to belong to this set is it is of the form A of X minus the divisor times something, some polynomial. And why Q of X? That's because I believe that whatever polynomial makes that happen, that's probably going to be our quotient. So I think that whatever polynomial in this set has the minimum degree, that's going to be the remainder we want. And the P of X that gives us that remainder, that's going to be the quotient we want. And now we're going to show that all of those things are true, that those really are the objects that we want. All right, so now our goal is to show that R of X really is small enough. In other words, the degree of R of X is less than the degree of B of X. Because what we already know, based on the previous equation, we know that A of X is equal to B of X, Q of X, plus R of X. So if we can get the degree requirement down, we're done. All right, so our approach is going to be, assume that that's not the case. So assume, by way of contradiction, that the degree of R of X is equal to M, and M is greater than or equal to the degree of B of X. And let's also let the degree of B of X equal N. Okay, so in other words, M is greater than or equal to N. And just so that we have something to play around with here, because it's kind of comforting to be able to play with some actual polynomials, even if they have symbols for coefficients, let's let B of X equal B0 plus B1x, etc., up to Bn x to the n. And on the same note, let's let R of X equal R0 plus R1x, etc., up to Rm x to the m. Sorry, that should be an m there. My pen's kind of skipping now. All right, so this gives us a little bit of a foothold to play with. And remember, we're assuming that the degree of this term is greater than or equal to the degree of this term. And the whole question is, can we get a smaller remainder? I'm just going to put that in brackets. Can we get a remainder of smaller degree? Because if we can, then we've reached a contradiction and our proof will be complete. So given this is one of our remainders, can we get this down to a remainder of even smaller degree by taking out some bundle of these? Okay? And I think the answer is going to be yes, because this is a term of smaller degree or equal degree to this one. So I think I can multiply B of X by an appropriate polynomial so as to get a term of Rm x to the m that I can then subtract. So that's going to be the idea. I'm going to multiply B of X times something in order to get a term of Rm x to the m as the leading term over here. So we're going to consider B of X times, and then let's just do a little scratch work over here. What would it take to multiply by Bn x to the n and get, that's a question mark there, and get Rm x to the m? Well, I think I'm going to need to multiply by R sub m so that I will have a coefficient of R sub m there. So I think I need that part. So I need an R sub m. I also need to get rid of this B sub n. To get rid of it, because I'm assuming the degree is n, I know that B sub n is non-zero, so I'll multiply by its inverse. That's the nice thing about working in a field, is I can eliminate that coefficient by multiplying by its inverse. And then to take care of the x's, I think I'll multiply by a power of x, but which power of x gets me from x to the n to x to the m? Well, this one has m minus n more x's than this one, so I think x to the m minus n will be the ticket. And that's valid because m minus n is greater than or equal to 0. Okay, so that's just my little scratch work over here. That doesn't have to be considered part of the proof. It was just me working something out. So we're going to consider b of x times rm bn inverse times x to the m minus n. All right, we know this is a polynomial. This is a polynomial whose leading term is, well, the leading term of b of x was bn x to the n times rm bn inverse x to the m minus n. That's going to give us the leading term of this new polynomial. And that's going to be rm, and then my bn's go away because I've got the inverse there, and then x to the n times x to the m minus n, that is just x to the m. So that is my leading term, and that's perfect because now when I subtract that from r of x, that's going to eliminate my leading term, and I'm going to end up with something of lower degree. All right, so that means, and I'm not going to belabor this too much by working out all of the symbols for b of x and r of x, but when we subtract r of x minus b of x times rm bn inverse x to the m minus n, we get a polynomial of degree less than m. Okay, but that polynomial, r of x minus b of x times the rest, that is, well, r of x was equal to a of x minus b of x q of x, so that's a of x minus b of x q of x minus another multiple of b of x rm bn inverse x to the m minus n. And that's equal to a of x minus b of x times something, that's b of x times q of x plus rm bn inverse x to the m minus n. And that polynomial, it belongs to S, and it has degree less than m. And that contradicts our assumption that m was minimal. So that contradicts the minimality of m. So now we have a contradiction. And what is the assumption we were contradicting? We assumed by way of contradiction this thing, that the degree of r of x was m, and that minimal degree was greater than or equal to the degree of b of x. So our minimal degree remainder has to have degree less than the degree of b of x. All right, so wrapping this up, therefore, there exist q of x and r of x in f bracket x such that a of x equals b of x, q of x plus r of x, and the degree of r is small enough. Degree of r of x is less than the degree of b of x. But what I haven't proven is uniqueness. What about uniqueness? Well, the proof of the uniqueness clause, that there's a unique quotient and remainder satisfying these conditions, is actually pleasantly quite a bit more straightforward than what we just did. We're just going to do the standard thing that we do when we try and prove an object is unique. We're going to assume that there are two of them and prove they end up having to be the same. All right, so let's assume that q1 of x and r1 of x and q2 of x, r2 of x are two quotient remainder pairs satisfying the conditions of the theorem. Okay, then what does that mean? So that means that b of x times q1 of x plus r1 of x, that has to be equal to a of x, which must also be equal to b of x times q2 of x plus r2 of x. So these have got to be the same. Let's start there and see if we can make some hay with that. So b of x q1 of x plus r1 of x equals b of x q2 of x plus r2 of x. Now, I think at this point, a nice thing to do would be to gather up anything having to do with b of x. Any term including b of x, let's get them together. So b of x times q1 of x minus q2 of x, and I'm going to put my two remainders on the other side, equals r2 of x minus r1 of x. Now remember, we assumed that these quotients and remainders satisfy the conditions of the theorem. So one thing we know is that degree of r1 of x is less than the degree of b of x, and so is the degree of r2 of x. That is also less than the degree of b of x. Both those things are true. So that means that when I subtract r2 minus r1, I'm still going to get a polynomial whose degree is less than the degree of b of x. Because if b of x is, for example, cubic and my remainders are both quadratic, well, subtracting two quadratics is never going to give me a cubic. It could give me a quadratic or a linear or a constant or zero, but never a cubic. So the degree of this difference definitely going to be less than the degree of b of x. But over here, I'm multiplying something by b of x. So if I'm multiplying something by b of x, common sense tells us that the product is going to have degree greater than or equal to the degree of b of x, because I'm starting with something of the degree of b of x. So if I multiply by a cubic by something, I'm going to get at least a cubic. That's what common sense tells us. There is one case in which common sense fails, and that's if we get 0. If the thing that we have over here in the brackets, q1 minus q2 is 0, then our degree drops to negative infinity, because this whole thing is 0. And that's the only way these two things are going to be able to agree, because this has to have degree less than the degree of b of x. The only way we can get a degree less than that of b of x over here is in that special case where the product is 0. And that's when q1 of x equals to q2 of x. That's the only way this is going to agree. And if the product over on the left is 0, then on the right we must also have 0, which means we must have r1 of x equals r2 of x. And that's the uniqueness proof. For these to agree, the q's have to agree and the r's have to agree, which means there really is only one quotient and only one remainder that will be suitable for a given a of x and b of x.